The vertical axis in a phase diagram of pure substances often represents the pressure. What is this pressure? In the case of the liquid-vapor equilibrium, discussed on this slide, the definition of pressure is very simple. It is the pressure of the vapor phase in equilibrium with the liquid phase. We also say it is the vapor pressure of the liquid or the vapor pressure above the liquid. On the next slide, where we focus on the solid-vapor equilibria, the pressure is the pressure of the vapor phase in equilibrium with the solid phase. To provide a little more clarity to the concept of vapor pressure, let us carry out the following thought experiment, starting with an evacuated container at some temperature T. By evacuated, we mean that there is nothing in the container, hence the pressure is that of vacuum, or zero. Let us assume we introduce in this container a substance A that is stable in the liquid state at temperature T and ambient pressure, and seal the container from the surroundings. What would we expect to observe? Initially, the substance A is only present in the liquid state, and since there are no molecules above the liquid, the pressure acting on the liquid is actually zero. However, when we examine the phase diagram, we see that at very low pressures, the gas phase should be stable. So, molecules from the liquid phase spontaneously vaporize, thereby increasing the pressure in the vapor phase that appears. With time, as shown by the arrow in the phase diagram and in the evolution of the system, more and more molecules of A go from the liquid phase to the vapor phase, and the pressure increases. The pressure actually keeps increasing until the system reaches the state defined by the blue point on the phase diagram. At this state, the liquid and the vapor are in equilibrium and coexist in the system at temperature T. The pressure of the vapor phase in such a state is called the equilibrium vapor pressure above or of the liquid, or more simply, the liquid vapor pressure. Unless heat is transferred into the system or out of the system, leading to a change in temperature, the system would remain at this pressure. That is, the system has reached equilibrium. Note obviously that transferring heat into the system, the temperature of the system would increase and the vapor pressure above the liquid will increase. Conversely, heat taken out of the system would lead to a decrease in temperature, hence to a lower vapor pressure. Note also that the equilibrium vapor pressure of the liquid does not depend on the amount of liquid. Obviously, if an insufficient amount of liquid is introduced in the container, the equilibrium vapor pressure will never be reached. The same would hold true if the container was not properly sealed from the surroundings, and if the water vapor could escape from the system. In the latter case, water would continue vaporizing, and eventually all the vapor would be lost to the surroundings. Note that the equilibrium vapor pressure of a liquid cannot be lower than the pressure associated with the triple point, and cannot be larger than the pressure associated with the critical point. Below the triple point temperature and above the critical point temperature, the liquid is never stable. So the equilibrium vapor pressure of a liquid can only be defined in this temperature range. The equilibrium vapor pressure of liquid water is shown here as a function of temperature. Note that for water, as for any liquid, the equilibrium water pressure is equal to 1 atmosphere at the normal boiling temperature. In a few slides, we will learn how to derive an equation that represents such a curve of P vapor versus temperature. We can repeat the experiment described on the previous slide at a temperature below the triple point, where the liquid phase is never stable. Introduction of a solid substance in an otherwise evacuated container leads over time to sublimation of the solid until the vapor phase develops an equilibrium pressure. This pressure is called the equilibrium vapor pressure of the solid or above the solid. The equilibrium vapor pressure above the solid is obviously smaller than that of the liquid and only depends on temperature. We can now turn our attention to the solid-liquid equilibrium coexistence curve. In this case, the word pressure takes a different meaning than for the liquid vapor and solid vapor equilibria. In the present case, the pressure must be viewed as the pressure externally applied to the solid and liquid phases in equilibrium. One way to apply such a pressure would be to immerse our two-phase, that is, the solid-liquid system, in a cylinder containing an inert gas, and pressurize the inert gas by pushing a piston down the cylinder. Such an experiment would show that the temperature at which the solid and the liquid phases are in equilibrium is a function of the externally applied pressure. We will see that while the temperature of fusion generally increases with the applied pressure, what we will call the fusion pressure, for water the situation is reversed. An increase in pressure leads to a decrease in melting temperature.